All right, welcome back. So this topic is 193009. This is core thermal limits. All right. These are going to be 8. We're going to go over 8 problems. They're all the same, so we'll go through the last few rather quickly. These will be calculation problems, and these are what are referred to as ratio problems. There's 2 different types of ratio problems in this topic. One of them will be where power is changing, and the other one will be where power and coolant temperature are constant. These 8 will be where power and fuel centerline temp or fuel coolant temperature are constant. So let's get started. Refer to the drawing of a fuel rod and coolant flow channel. See figure below. All right, we got a coolant flow, we got the fuel pellet, we got the cladding. We've all seen that before. All right, given the initial core parameters, 100% power, 500 degree coolant temperature, and 3000 degree fuel centerline temperature. So that looks good, looks normal. What would the fuel centerline temperature be if the total fuel to coolant thermal conductivity doubled? Total fuel to coolant thermal conductivity doubled. So assume reactor power and coolant temperature are constant. So reactor power, we're assuming that's constant, right? So Q dot is going to equal Q dot 2. Q dot 1 is going to equal Q dot 2. So if you recall from your equation sheet, another equation for thermal power is going to be U1A1 delta T1. And that's going to equal to U2A2 delta T2. All right. Now the area is going to be the surface area of the clad total. And that's just not going to change, right? So we'll go ahead and say that A1 equals A2. And now what this is telling us that the fuel to coolant thermal conductivity doubled. So this factor is kind of a catch-all, and one of the things it catches is the fuel to coolant thermal conductivity has doubled. So we'll just go ahead and say that U2 is going to be equal to 2 times U1. Now we can rewrite the equation as U1 delta T1 equals 2 times U1 delta T2. All right. Now we can tell that U1 is going to cancel out. And now we've got delta T1 is going to be equal to 2 times delta T2. And so we are looking for delta T2 is going to be equal to temperature centerline 2 minus temperature of the coolant. Okay. So I'm going to go ahead and say temperature of centerline 1 minus temperature of the coolant divided by 2 plus temperature of the coolant is going to be equal to T centerline. Sorry, I messed it up. Then we're going to take that over here, and temperature of the centerline 1 is going to be 3000 degrees. I'm going to move that over a little. So 3000 degrees minus 500 degrees divided by 2 plus 500 degrees, and that will be equal to temperature centerline in state 2. So don't need a calculator for this. It's going to be 2500 divided by 2. And that's going to be 1250 plus 500 is going to be 1750. 1750 degrees Fahrenheit. And indeed, the answer is 1750 degrees Fahrenheit, and that's the correct answer. All right, so we'll move on and do another one real quick. We'll go to page 16. Here's another one. Refer to the drawing of the fuel rod and coolant flow channel. Given the following core parameters: 100% power, 500 degrees coolant temperature, 2500 degrees fuel centerline temperature. What would be the fuel centerline temperature if a total fuel to coolant thermal conductivity doubled? Okay, so again, yeah, we've got Q dot equals Q dot 1 to 2. All right, U1 A1 delta T1 equals U2 A2 delta T2. All right, so the A's area hasn't changed, but we know that instead of we know that U1 no, we don't, sorry. We know that U2 is equal to 2 times U1. So now we go U1 delta T1 is equal to 2 times U1 delta T2. Now the U's cancel out. And we've got delta T2 is equal to delta T1 divided by 2. Okay. And that is going to be equal to 2500 degrees minus 500 degrees divided by 2. And that's going to be equal to 1000 degrees. So temperature center line 2 minus temperature of the coolant is going to be equal to 1000 degrees. So we'll have to add temperature of the coolant in state 2, which is stay the same, right, because we're constant. And now we say temperature center line at state 2 is equal to 1000 plus 500, which is 1500 degrees Fahrenheit. The answer is delta. The answer is delta. Okay. Pretty easy, huh? So we'll keep going through them, see if anything pops up to make it really hard. Here's 1594. For the drawing of the fuel channel, reactor power is 100%, coolant temperature is 500 degrees, fuel center line temperature is 2700 degrees. All right. The conductivity is doubled, right? So I think we can skip on down to delta T2 is equal to delta T1 divided by 2. Okay, so temperature center line at state 2 is equal to delta T1 divided by 2 plus temperature of the coolant, because coolant is constant. So temperature center line 2 is going to be equal to 2200, that's 2700 minus 500, divided by 2 plus 500 degrees Fahrenheit. Okay, and that is 1100 plus 500, and that's going to be 1600 degrees, and the answer is C. Okay, and we'll move on to the next one. Where is it? Here it is. 1994. We're only at 80% power. Does that matter? Well, maybe. It might matter. So give the thing a good read. Give the following initial core parameters. Reactor power is 80%. Coolant temperature is 540. Fuel centerline temperature is 2540. What would the fuel centerline temperature be if the total fuel to coolant thermal conductivity doubled? All right. So I think we can do this. Temperature centerline at state 2 is going to be equal to delta T1 divided by 2 plus temperature of the coolant. Alright, so with the fuel centerline temperature is going to be 2540 minus 540 divided by 2 plus 540. So that's going to be 2000. Divided by 2 is 1000, so 1540. The answer is indeed delta. Okay. If you want to see how I got that, just go on up. We'll skip through these rather smartly. So I think what we saw here is even at 80%, it didn't matter. I mean, the fuel centerline temperature, as long as reactor power is staying constant, this doesn't matter. Now, there will be a time where reactor power will change, and we'll have to do a ratio, and that will matter. Kind of hard to get that answer. All right, for the fuel rod drawing and coolant flow channel, given more parameters at 60% power, you had fuel centerline temperature 2500 and coolant temperature 560. What would be the fuel centerline temperature if the total fuel to coolant thermal conductivity again doubled? Okay, assume reactor power and T coolant are constant. All right, so we go temperature centerline 2 is going to be equal to delta T1 divided by 2 plus temperature of the coolant. So temperature centerline 2 is going to be equal to 2500 minus 560 divided by 2. So now this particular gentleman who's writing this test, or lady, is wanting you to miscalculate, so be careful. Don't do what I just did and write a 5 messily, if that makes sense to you. So I've got to use a calculator for this. 2500 minus 560. That's going to equal 1940. Divide that by 2 is 970 plus 560. It's 1530. 970 plus 560. See, I'm being messy there. 560. And that's going to be equal to 1530 degrees Fahrenheit. So I think we can see that if we doubled our thermal conductivity, the fuel centerline temperature will go down. If we doubled our fuel thermal conductivity, the fuel centerline temperature will go down a little less, or a little more than half. So that's good. It's a good thing to probably know. So there's another one, 2395. Is that one? Yeah. Reactor shut down with the following parameters. All right, now this one's a little different. We got to shut down reactor. So we're on decay heat. Does that matter? Well, it shouldn't. All right, so let's see. Reactor shut down with the following parameters: 780 and 320. Centerline temperature and coolant temperature. What would the fuel centerline temperature be if the total fuel to coolant thermal conductivity doubled? We're going to say it's going to be less than centerline temperature now, because the conductivity is more, meaning heat can pass through from this point to this point easier, twice as easy. All right, so we'll do it from the beginning. We'll, I guess derive, if that's what you want to call it. Q dot 1 equals Q dot 2, heat transfer. U1 A1 delta T1 equals U2 A2 delta T2. Alright, remember that A1 equals A2, and U2 is equal to 2 times U1. Alright, so now we go delta T2 is equal to delta T1 divided by 2. Temperature center line at point 2 is going to be equal to delta T1 divided by 2 plus temperature of the coolant. And that will be equal to 780 minus 320 divided by 2 plus 320. Got my phone. So we've got to figure that out. 780 minus 320, divide that, 320, divide that by 2, then add 320 to it. It's going to be 550. Answer A. Temperature, center line at state 2 is going to be 550 degrees. Answer A. Excuse me. So next problem should be the same. So this one doesn't give you, this new one doesn't give you this assumed decay heat level and coolant temperature constant. So maybe that's different. But we'll see. It's got the same drawing. Further drawing of fuel rod and coolant flow channel. The reactor shut down at the beginning of cycle with the following average parameter values: 780 minus 440. Will the fuel centerline temperature be at the end of the fuel cycle the same coolant temperature? And they just tell you reactor decay heat conditions if the total fuel to coolant thermal conductivity again doubles. Okay, so temperature center line 2 is going to be equal to delta T1 divided by 2 plus temperature of the coolant, right? Temperature center line 2 is going to be 780 minus 440 by 2 plus 440, and that is going to be in degrees Fahrenheit. Temperature center line 2, 780 minus 440 divided by 2, it's going to be plus 440. I have 610 degrees. 610 degrees. Alright, at the risk of boring you, I'm going to keep going. Again, we're back to 50% power. Alright, so we've done these before. I'm just gonna kill it out, man. Given the following core parameters: reactor power 50%, T coolant's 550, fuel center line temperatures 29750. Will the fuel center line temperature be if the total fuel to coolant thermal conductivity doubles? Again, doubles, okay? So temperature center line at state 2 is going to be equal to delta T1 divided by 2 plus temperature of the coolant, right? Temperature center line 2 is going to, equals 2750 minus 550 divided by 2. That's going to be 2200 divided by 2, 1100 plus 550, and that's going to equal 1650. And here's one where power changes, so we'll get to that with the next video. Oh, and that was the last one we're going to go over. So thanks for watching. So these were an 8 question out of 35 question test bank. And remember, this is for 1 question on your GFES exam. So keep that in mind when you're studying. Good luck and God bless.